Hopefully there's no IT issues. Now we've got 3 students away, so I'm hoping this will screen capture. Now, this activity was a little bit of a failure because I set up the scenario where the path difference was 0.44 meters, and it wasn't a whole integer of wavelengths, nor was it a half integer. It was somewhere in between. So I scribbled this down. This is what wasn't captured on the screen. You wouldn't get that in a test, all right? If you're solving for n, it's either going to be a 0.5 or a whole integer, okay? This one's a little bit tricky, and I'll leave it to you as an extension. We put a really nasty question in the 2018 test that involved that kind of extension, solving for the path difference equaling a value, and you had to do a little bit of rearranging. Matthew Gamble, could you please close it? Thank you. So, I just want, if you have some room on the following page, at the bottom of page 7, let's just do a nicer example, okay? Let's suppose we have a speaker here and a speaker here, and you stand directly in the middle, okay? Now, we won't do any wave equation mumbo jumbo. Hugo, please close it. No, close it, please. Let's just say that it's pumping out a wavelength of 0.5 meters. So it's about 700 or 800 hertz, okay? Now let's say that this person is in the middle, 10 meters apart are the speakers, and so straight away each of the path lengths, L1 is 5, L2 is 5. In that scenario, there is no path difference. The path difference equals 0, okay? And so n lambda equals 0, n equals 0. So he is going to hear a loud region. Both of the waves, both of the speakers they're in phase, right? So a crest and a crest is meeting, so he'll hear a loud pressure, and then a trough and a trough is meeting, all right? So that would be an area of constructive interference. Now, let's move this person. Let's place him. Now, you could keep that diagram there if you want. Let's just draw him. Let's suppose that he moves here. And I'm going to make the maths really, really easy. So there's not going to be any 1.84 crap. Let's just say that he moves so that he is 3.5 meters from the right speaker. And then by arithmetic, he must be 6.5 meters from the other speaker. Okay? So let's figure out the path difference here. So the path difference equals, doesn't matter which number, you just take the small number from the big number. It doesn't matter, we want a positive value, okay? 6.5 take 3.5, that is 3 meters, okay? So that means this length is a whole 3 meters. 1, 2, let me try that again. 1 meters, 2 meters, 1, 2, 3 meters. So the left speaker has travelled 1 wavelength, 2 wavelengths, 3 wavelengths further. Okay? 6, yes, thank you. Oh dear, let me try that again. 6 wavelengths. I thought I'd set lambda to 1. Let's try that again. Try and draw 6 wavelengths here. Ready? 1, 2, 3, 4, 5, 6. Perfect. Thank you. So I hope you can see that. The path difference, the left speaker has had to travel an extra 3 meters. It has to have travelled an extra 6 wavelengths. But again, if we do the maths, the n lambda, so n equals 3 over 0.5, that is 6, okay? Whole number, so in phase, constructive interference, he will hear loud. One other way to visualize this is that when he was standing in the middle, he was at n equals 0. Now, hear me out here, follow my logic. If he moved a quarter of a meter one way, then L1 goes up, L1 goes down by a quarter, L2 goes up by a quarter. So he only needs to move a quarter of a meter to get to the next n equals 1. Right? Because one goes down by a quarter, one goes up by a quarter, and so the difference is half a meter, which is a wavelength. Okay? So really, we could now probably draw a dashed, N1, N2, N3, N4, N5, N6. That one I haven't been able to put that in. Let's just go 1, 2, 3, 4, 5, 6. That's where he is now. 6. 0, 1, 2, 3, 4, 5. So it's a bit weird to think that as he's walking from 0 to 6, he's going to hear 7 loud regions. Because we'll count where he initially is. So he's going to hear it loud, then quiet, then loud, then quiet, then loud, then quiet, then loud, then quiet, then loud, then quiet. Okay? So N6 is also telling us how many regions he's moved through. So he's moved through 7 loud and 7 quiet. Okay? I could have just as well as done a 3.25 and a 6.75, and then we might have gotten a half integer wavelength. Or, 3.625. Okay? But I just wanted to start off, I should have started with a much nicer example than an ugly one. Now, we can't go too difficult. What we typically do is then go, let's put the person here and then move them so that they're here, and then you just do Pythag. So here's your L1 and here's your L2. I mean, that's pretty much as hard as it gets. But remember from the applet, you could place this person anywhere. Ready? I'll just go there. Put him there. He could stand there. And that, it doesn't matter where he stands, you've got L1 and L2. Right? And then you go, well, what is the path difference? Is it a whole integer of a wavelength or is it a half integer of a wavelength? Okay? Now, the next phenomena. From superposition of waves. If our wave is in phase, look what I've got. I've got wave 1 and I've got wave 2. And then that's the sum of them. Okay? And so we're going to combine those two waves and we see that they're in phase. We get peaks meeting peaks. We get troughs meeting troughs. Okay? Now, this is a bit weird, but if we change one of the frequencies by a certain frequency, it's going to be out. And so they're going to be out of phase. But then at a certain time, they'll come back into phase. And then they'll go out of phase again, they'll cancel, and then they'll come back into phase. Okay? And this is known as a beat frequency. So I've borrowed this image. Okay? Have a look below. This is a bit tricky. You would not be expected to draw the superimposed wave because that's just too nasty. But have a look. At point X, you can see that they are in phase. Okay? And so we get a large superposition. But if I go to point Y, have a look. We've gone, frequency 1 has gone through 1, 2, 3, 4, 5, 6 wavelengths. Frequency 2 has gone 1, 2, 3, 4, 5, 6, 6.5. Okay? So it's a full half wavelength out. And that's why we get a crest meeting a trough. We get alternating regions of constructive and destructive. Okay? Now there's a really simple equation for what you will hear, but let's go to the demonstration at the back. We've got 2 speakers that are pumping out 100 hertz. Okay? Now, a bit blurry, but that'll do. So they're both pumping out 100 hertz. And the oscilloscope, if you can have a look, is measuring the intensity of both. Okay? So 100 hertz and 100 hertz. Now, if I change one of them by 1 hertz, then in 1 second, this guy is going to put out 100 waves. This guy is either going to put out 99 or 101. Okay? So let's just change. All right, here we go. Ready? by 4 hertz. So I'll drop this to, there we go. Okay? So this one's pumping out 100 in a second, this one's pumping out 96 in a second. Right? Now again, see that equation in the bottom left corner of the screen. The beat frequency is simply the sum of the two. Sorry, the absolute value of the difference. Okay? So here's the problem though, and this is the tricky one. I'm measuring a beat frequency of 4 hertz. Bum, 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 1, 2, 3, 4, 1, 2, 3. It's probably better to count. A beat frequency of 4. Now here's the thing. If I told you one of them was 100, because it's an absolute value, the other one is going to be different by 4. We don't know whether it's 96 or 104. Yeah? We don't know. So for example, that was 96. Let's change this one to 104. Good. Alright. I've gone from 4 hertz under to 4 hertz over. The beat frequency is still 4 hertz. Okay? Now, an old school example of your twin prop planes in World War II, they would be driven by carburetors pumping fuel in, and they're spinning at a certain RPM, right? And what the pilot would do, if one prop is spinning and the other prop is spinning, they might hear a beat frequency, which means that one of the propellers is spinning a little bit faster or slower, yeah? Now, you don't really want your two engines putting out different amounts of thrust. So they would either throttle up or throttle down one of the props, and the beat frequency would either increase, meaning that you're going away from, you're increasing the beat frequency, so you're increasing the differences. Oops, wrong way. Bring it back, and it would and you would decrease it until you didn't hear a beat frequency. Once your beat frequency is 0, then the two frequencies are equal. A more relevant application is when you tune an acoustic guitar. Who here knows how to tune a guitar without a digital tuner? You've got one string, and then you hold the next string in a certain position, and they should make the same frequency. If they don't, you will hear a beat frequency, and so you slowly increase the tension, decrease the tension, until that beat frequency goes away. At that point, you know that they're at the same frequency. They might not be in tune, but you know that they're vibrating at the same rate. Yes?
If the pilot went too far, couldn't he or she accidentally have one that is not faster?
Well, you're right. So what can we hear? And we can hear a tone of up to about 20 to 30 hertz before the beat frequency disappears. So we'll have a look. Let's go up to 30 hertz. Guys, just Faraz asked a question, if we go too far, let's go to a beat frequency of 20 hertz and tell me if you can hear it. So, I'm going to pump this one up to 120 hertz. Ooh. That's a beat frequency of 20. Let's bring it down a bit. That's 10 hertz. You can hear, and then let's bring it closer. So that's in your plane. 6 hertz, alright, let's throttle back one of the engines. 3 hertz, 2 hertz, throttle it back. Now both your propellers are spinning at the same rate. Okay? If you go too far, it's going to come back. Whoop. Let's bring it back forward. Alright, now our propellers are both throttled at the same frequency. Okay? Alright. Let's go and drop some bomb. Okay. So, that is beat frequencies. Let's have a look at this question here. Please, and thank you. Now, it doesn't really matter which one you pick. We've got, let's just call it F1. Let's call that FB. Okay? Let me just find my solution. No. Where are my beat frequencies? There they are. Okay, so Okay, so we've got 2.5 equals the absolute value of 200 minus F2. And because it's an absolute value, that's why we get F2 is going to be 200 plus or minus 2.5. So it's either going to be 197.5 or 202.5. Okay? Hertz, HZ. The tension in the first string. Now, we're going to learn about tension. Tension actually increases the restoring force. Matthew Gamble, close it, please. Tension increases the restoring force, which is the force that tries to return your particles back to equilibrium. So if they return back to equilibrium at a quicker rate, the speed in the string is going to increase. There is an equation which we will learn. It's that V is equal to the square root of tension over some property called that's the linear density. But basically, we can see that V is proportional to tension. If I increase tension, I increase V. And so from V equals F lambda, if I increase tension, I'm also going to increase frequency. So that's your classical guitar string. You're strumming your guitar. If you tighten the string, it's going to increase your velocity. It's going to make a higher frequency. So, and then if you loosen it, the frequency decreases. Okay? By the way, that's not part of this question, but essentially, if we increase T, that means that F1 goes up. Okay? Now, we observe our frequency to now be 4 Hertz. So let's just draw this FB equals. So now we have 4 Hertz equals tension in. Now the question is what must F2 be? So we started with a difference of 2.5 Hertz, and then we increased F1, and the difference was greater. I always struggle to explain this equation because there's that damn absolute value. Basically, we're getting further from F2. All right, so if you're increasing the frequency and you're getting further from F2, it had to be 202.5. Because if we increase 202.5, then the difference from 200 gets larger. Have a think. If it was 197. Oh, what? No, that was F.
So it has to be 197.5.
Oh, sorry. We're saying F. It's either that one or that one. Yeah, we're increasing 200. Ah, yes, you're right. Okay, so if we're increasing, my apologies, if we're increasing this, then if it was at 197, then the difference would increase. If F2 was 202.5, then the difference would decrease. Okay? I'm not quite sure if there's a mathematical way to sort of prove that other than say, if we were to increase F1, then the difference between 197.5 and that frequency would increase, yes?
Also increase it to 206.5.
Okay, so that's why the question will often say it's slowly increased. If you're strumming your 2 guitar strings and then you just go without listening or strumming, then you're going to go way beyond, and then you'll get to that set. So you've got to do it slowly, and so you slowly listen for the changing in the beat frequency, and then eventually it's going to get to 4. Then it's just going to get faster and faster and faster. So what you're saying is if you were below and you get to 0 beat frequency and then past it and then you listen to it again, yes, you run that risk. That's why I slowly change the frequencies and you're listening for how the beat frequency changes. Okay? It's a little bit of a tricky thing. But just remember, beat frequencies, this is a phenomena, and the equation for it, where is it? There it is. The equation's pretty simple. It's just the difference between the 2 frequencies gives you what the beat that you'll hear. Yes.
So say like on a plane, could you go the wrong way and then still get rid of the beat frequency?
Well, no, you couldn't go the wrong way because the beat frequency would increase. Okay? So that's why, as I said, you've got to be careful. If you get to 0 and keep going, the beat frequency is going to return. It's going to drop to 0, and then it's going to start to raise again. Okay? Could we please continue on to the following page? Okay? Now, I want to get through this so that next week we can do strings and harmonics and there'll be a prac. So I just want to talk about, there's a few different ways that an object can vibrate. Okay? A free vibration is when you displace an object and it will just start oscillating from its equilibrium point. Okay? It's left to oscillate or vibrate by itself. Okay? A tuning fork is a perfect example. And I wasn't going to get the tuning forks, but I am today because this is where we're at.
Yes. Where's your test? Where's your test?
So, guys, here are our tuning forks. Now, you might not know this, boys. Shh. And I generally try and take one off just to show you that it's definitely, you can't really hear it because the tuning fork has a small surface area. And so when you strike this tuning fork, it's only displacing a small amount. Now, all right, you put it up to your ear, you can hear it. The two prongs are vibrating backwards and forwards, so this is called a free vibration, all right? You can displace them by plucking them like that, and it's just going backwards and forwards, okay? It vibrates about their mean position, the restoring force brings them backwards and forwards, and it's going to vibrate at its natural frequency. This one is 355 hertz, so if we could view these little prongs, they would be oscillating 355 times a second, okay? Can you think of any other examples of a free vibration? Anyone? Anyone? Have a think. Can you think of any object that will just oscillate about its equilibrium point? Yes?
Guitar string.
Guitar string. Good. Let's just go stringed instruments. I also, kid on a swing. Okay? If you displace a kid from its equilibrium point, then they will just oscillate backwards and forwards about their mean position. Okay? It's a conversion of potential to kinetic. Same with this. It's instead of gravitational, kid on a swing is gravitational potential to kinetic. This is elastical potential because when you compress something, it doesn't want to be there and so it restores back. Okay? Now, can you think of any other pendulums? A pendulum. I see people moving about. 9:45. Is it time for me to kick you guys out?
Yeah.
And you all have a test now, do you? Some of you. Okay. Well, I was hoping to get to forced vibrations, but oh well, we'll get to that in tomorrow's lesson. Thank you very much for your attendance.